Hey everyone, my name is Max Wasserman. I'm a PhD student at the University of Rochester in the Computer Science Department. Today I'm going to be talking about graph structure learning with interpretable Bayesian neural networks. And I did this work with my advisor, Gonzalo Mateos. So what does this talk about? We want to make edge predictions with uncertainty quantification, right? So whereas in traditional GSP, right, we study signals defined on or filters constructed with some known graph, but often the graph is not observed. And so graph structure learning attempts to learn graphs from the nodal observations, and there are two main approaches. One is the model-based approach, which solves an optimization problem, right? And the returned solution is our graph estimate. And the second is an unrolling-based approach, where we construct a deep network using the model-based solution iterates. Both of these, typically only provide point estimates of graph structure, and so the goal in this work is to provide a point and uncertainty estimate of graph structure from these nodal observations. So how are we going to do that? So here's a quick outline of the talk. First, we're going to develop a point estimate function. Right? We're going to do this by posing and solving an inverse optimization problem to estimate the graph structure from the nodal observations. Then we're going to unroll the solution iterations to form a deep network. Then we're going to make it Bayesian. We're going to put priors over our parameters. We're going to perform inference, and we're going to derive point and uncertainty estimates over these unobserved edges, right, from the posterior predictive distribution, which we'll introduce later. So some quick notation and background on graph signal processing, right? We have some graph G, where there's unobserved graph G and adjacency A. We collect node signals into matrix X, where the ith row is the ith node's signals. We use X, these node signals, to form Euclidean distance matrix E, right? And we work with the undirected graphs without self loops. And so we can take advantage of the symmetry and reduce dimensionality. Right? We can introduce this lowercase a to represent the upper triangular part of the adjacency A, and lowercase e to represent the upper triangular part of the Euclidean distance matrix E. So the last concept we need to introduce is the total variation of our signals X with respect to some graph G. Right? Intuitively, this is a non-negative real number, which provides a measure of smoothness of the signals on the graph. It's defined as the trace of X transpose L, being the Laplacian matrix, X, right? And Calafelias in 2016 showed this connection between this smoothness interpretation, right, from the definition, and a sparsity interpretation, right? He showed that we can equivalently rewrite it as the one norm of the Hadamard product of the adjacency and the Euclidean distance matrix. And so we're going to leverage this formulation in our graph recovery problem to come. So we want to produce this point estimator. We're going to start with this model-based approach, right? So our goal is to identify some undirected graph G from the signals X such that they're smooth on G. And so why are we using this idea of smoothness, right? The reason is many real-world graph signals are smooth, right? They have total variation being small. So for example, in sensor networks, right, the graph signals that we tend to observe tend to have low total variation or tend to be smooth. Same thing with product rating networks, right, where we have people, and the products that they've rated, right? We tend to find those signals on top of these to be smooth. Okay, so how are we going to provide this point estimate function with the model-based formulation? Well, we're going to formulate and solve a convex inverse problem that takes the following generic form. Right, we search for an optimal point within a convex constraint set of admissible adjacency matrices, that's calligraphic C, and our objective is decomposed into two high-level terms. Right, one, the data fidelity term, which is a function of both our optimization variable A and our Euclidean distance E, right, our data. and a regularization term, right? A function of only our optimization variable. So a state-of-the-art convex formulation, right, for model-based graph structure learning is above. So it takes the same form, right? A data term and regularization terms. So here the first term is our data fidelity term, right? There's 2 A transpose E. And if you recall, right, this is the total variation of the data on this graph, right? This is adjacency A. Right, the second term is a regularizer to prevent isolated nodes. Here, S times A is simply the degree vector, right? And so we have a log barrier on the degree vector, and it's scaled by a regularization parameter, alpha. The next term is a 2 norm on the edge weights, scaled by a regularization parameter, beta. And then we bring in a non-negativity constraint into the objective. So we called this the alpha-beta formulation of the problem. And Kalfilias again introduced this equivalent reparameterization from the alpha-beta formulation to a new parameterization, which we call the theta-delta parameterization. Right? And the important point here, if you look at the very bottom expression here, is that by doing this, we have separability in the structure of the optimization problem. And by that I mean, inside of the argmin, we only have theta appearing, right? And outside of the argmin, we only have delta appearing. And because of this, we're going to find that only theta influences the sparsity pattern of the recovered graphs. So to solve this problem, to solve this bottom problem, we introduce iterations called dual proximal gradient descent, right? DPG iterations on the left here. And as a consequence of the separable structure of the reparameterization, right, the theta delta reparameterization, we see that the iterations only contain theta, right? Theta is the only parameter contained inside of these iterations. The sparsity pattern of the solutions are determined by theta independently of all other parameters, right? In this case, delta. And a higher theta tends to produce higher sparsity. I'm going to introduce this terminology that I'm going to come back to a few times. And I'm going to say theta is independently interpretable with respect to the sparsity of the recovered graphs. And I'm going to say this because theta determines the sparsity pattern independent of all other parameters. It acts as a bridge between prior information on sparsity and the value of theta. We're going to find this very useful when we do Bayesian modeling, right? Where we're going to use this bridge to produce informative priors over our parameters. Okay, so we produce this model-based point estimate function, and now we want to use unrollings, right? So there's kind of 3 steps in producing an unrolling, deep unrolling. The first is we assume some generative process that ties our data to the graph. The second is we propose some optimization framework and some iterative solution procedure for the inverse problem, right? Recovering the graph from our signals. Note that these first 2 steps we've already done, right? This is kind of the model-based graph structure learning approach. Right? Our DPG iterations are what maps, right, recovers our graph structure from our node signals. And finally, we unroll the iterative algorithm to motivate the deep network architecture. So if you look at the figure on top, on the left, we have some iterative algorithm, right? These are our DPG iterations. We repeatedly apply, right, some function here called h. And by enrolling it, what we mean is we associate an iteration in the iterative algorithm with a layer in a deep network, right? And importantly, we truncate after a finite number of steps. So we don't necessarily run to convergence, but we truncate after what we say D steps. So to produce this R deep unrolling, right? So we transform our regularization parameters to learnable parameters that we're going to learn with backpropagation on a data set, which we'll talk about in a moment. We'll truncate after DPG iterations, and we now approximate solutions, right? We're not necessarily running to convergence. And so the output of this unrolled DPG network returns approximate solutions. And in this case, this is the first graph structure learning neural network. And what I mean by that are layers of linear transformations and pointwise nonlinearities, right? Previous enrollings have typically had nonlinear transformations that were not pointwise. So for example, we had parameters that were in a denominator or that were multiplying each other. So we're going to find that that's actually going to help us in some gradient-based sampling. Okay, so unrolled DPG is a neural network function, right? It takes in our Euclidean distance matrices or data, and it returns an adjacency matrix A. Right, the gradients with respect to the parameters are well defined. We assume we observe a data set, right, which is simply pairs of Euclidean distances and adjacencies. In this case, we use unweighted graphs, right? So the edges are binary 0, 1. But if we want to use weighted graphs, all that would change is the likelihood. We subtract the mean, we drive through a sigmoid, and so our final 3-parameter graph structure learning neural network is as follows, right? This sigma delta gamma, right? This is our unrolling, minus b. And capital theta denotes our parameter triple, right? Theta, delta, and b. In this case, our likelihood is a Bernoulli likelihood, and the unrolling encodes the mean of this likelihood, right? This is kind of where the unrolling comes in. So now we're going to build a Bayesian model, right? Namely a Bayesian neural network. And so let me introduce kind of the basic ideas in Bayesian neural networks, BNNs. So a Bayesian neural network is a neural network with stochastic weights. We have a posterior distribution, which is the distribution over weights conditioned on the observed data, right? In this case, given by Bayes' rule, right? P of theta, given our data, proportional to the probability of the data given a specific value of the parameters, times our prior beliefs over that specific value of the parameters. We then can push the posterior distribution through the neural network to produce a distribution over predictions. Right, this is the posterior predictive distribution, right? And A tilde, E tilde, right? These are test samples. And so we can produce a distribution over the unobserved edges in a test sample by introducing and integrating out our the distribution over our parameters, right? The posterior. And then we can use this predictive distribution to derive a measure of uncertainty over our edge predictions. So the key ingredients in BNNs, right? We have a weight prior, P of theta. We have the likelihood, or the probability of our data, given a particular value of our weights, our parameters. And we have the posterior, right? Which is the distribution of the weights given our data. The typical difficulties in Bayesian neural networks and in kind of Bayesian models in general is one, how do we set the prior? Right, this is typically somewhat difficult to do. And two, how do we approximate the posterior, which is typically intractable? And we're going to go through what we do in both of these cases. Okay, so we want to produce a Bayesian neural network. And so the first thing we need to do is we need to solve kind of the prior difficulty. We need to set priors on our parameters. So we're going to use the independent interpretability of theta to do so. Right? So we're going to take a subset of our observed data, our observed Euclidean distances, E. We don't need to use any labels. And we're going to transform prior beliefs over sparsity to a prior distribution over theta by using this bridge concept of independent interpretability. So to see this concretely, look at the figure on the right. Right? We have sparsity, and we have our prior beliefs over sparsity. Right? We have some distribution which encodes our beliefs over sparsity before observing any data. So first we're going to discretize theta, across a couple orders of magnitude. And we're going to run convergent DPG, right, with each value of theta. Remember, the sparsity pattern of convergent DPG, or the iterations, only depends on theta. And so we can do this, right? So we can run our subset of inputs through convergent DPG. Each input, right, defines some recovered graph which has a edge sparsity, and we do this over a subset of them, right, a set of them. So we can plot a histogram of all the edge sparsities. We do this for each value of theta that we discretized. And what we're going to do is we're going to see how this histogram lines up or matches our prior beliefs, right? And those values of theta which most closely match our prior beliefs, we're going to assign high prior probability to. So you can see kind of theta of 10 negative 2, right? The second to the bottom here matches very well our prior beliefs, and so we're going to set a large amount of prior probability, whereas much larger values of theta don't match it very well at all, and so we assign it very low but non-zero prior probability. Now we still have to make priors over the other parameters, delta and beta. Here we make weakly informative priors. I'm not going to have time to exactly go into how we do that, but if you look into the paper, we kind of use the results of this approach to do those. It kind of comes naturally from this. Okay, so now we're going to, now that we have priors over parameters, we need to do inference, right? This is the second kind of difficulty. And so in this case, what are we going to do? We're going to use Hamiltonian Monte Carlo as a sampling-based approach to produce our posterior samples. Why can we do this, right? Typically, this is very difficult to do in BNNs, but due to the nature of the enrolling, right, we have very few parameters. It's very efficient to execute, and so sampling-based methods become quite appealing and tractable, particularly because we have informative priors, which tend to make sampling approaches work much better. Okay, so we have our posterior samples. We're going to marginalize out our parameters over some test sample, right? So tilde E, tilde A. This is the test Euclidean distance and test the unobserved edges. So we're going to introduce and marginalize out our parameters. This produces our posterior predictive. The way we actually interact with this posterior predictive is by sampling it. And so we have our tilde A to the M, right, the mth posterior predictive sample. And we use these to produce edgewise point and uncertainty estimates, right? This is what we've been after this whole time, right? And so to produce the point, the edgewise point estimate, we take it to be the expected value of the edgewise expected value of the posterior predictive, right, where a tilde A sub I is the ith edge of the unobserved adjacency A. And for uncertainty, we take the predictive standard deviation, right? And so kind of same idea. Okay, and if we follow this approach, and we can validate it on synthetic data, which we do. We use many metrics and random graph ensembles, and we show that this approach tends to provide excellent recovery, well-calibrated predictions. So, for example, if you look at the error, right, the magnitude, the order, it's around 1% error for many of our models, so it's providing excellent recovery. And if we dig even deeper, right, into maybe a subjective evaluation, so for example, here is a single test sample from the test set of the synthetic graphs that I just talked about in the last slide. So on the left is the label. This is the true label of the unweighted graph. In the middle is the predictive mean. Right? This is our estimate of the expectation of the posterior predictive. And on the right is the predictive standard deviation, right? Or estimate of the expected standard deviation of the posterior predictive. Now, In blue, I've highlighted some areas where our point estimate strongly matches the true label, right? So if you look at the predictive mean, if you look at those blue boxes, blue rectangles, and you look at the corresponding locations in the true label, they're very close, right? They match very closely. And in red, I've highlighted the areas where they disagree, right? Where we make some mistakes. And I can make it even clearer by removing the background here, right? And so hopefully it's clear, right, that in the blue boxes, right, where the mean, right, is approximately the label, we can see its predictive standard deviation tends to be very near zero over these regions, right? Hopefully that's clear, you can see that. And in red, where we make some errors, right, where we don't have an exact match between the predictive mean and the label, we tend to have much higher predictive standard deviation, right, our measure of uncertainty. And we can summarize this over all edges by using Pearson correlation, right, between the error and the predictive standard deviation. And if we do that, we see that we have a very strong association, right, between the standard deviation, the predictive standard deviation, our uncertainty estimate, and our error, right, which is what we want, right? In a predictive model, we don't have access to error when we make predictions, but we do have access to predictive standard deviation. And so if they're strongly correlated, we can use that instead of the error directly. Okay, so we can now test on real data. So for example, recovering sector graphs from S&P 500 stock time series, right? So here we have 82 stocks from 3 sectors. On the left, we see the names of some of the stocks in 3 sectors respectively. So we have communications, utilities, and real estate. The time series data consists of daily close prices, right, between 2014 and 2017, with about 1,000 observations. And we split the stocks evenly into train and test, right? For each split, we compute the input, 1 minus the absolute value of the Pearson correlation matrix. This is a dissimilarity matrix similar to Euclidean distance matrix, and a label, right, where the ijth nodes, in this case stocks, are connected if they're in the same sector, and 0 otherwise, right? This creates a block diagonal matrix in the true label adjacency. Then we run inference, right, using our DPG BNN, using this single training example. And if we do this, we see very good recovery, and we also see similar to our synthetic evaluation, that where we make mistakes, the predictive uncertainty, the predictive standard deviation tends to be higher. So on the left, we have our input. This is our dissimilarity matrix. This red outline, this is the block diagonal, where inside of it, there should be edges, and outside of it, there should not be edges. So our predictive mean, right, where it's white, that means this is true. We predict a true edge, we're closer to 1, and where it's 0, where it's black, it's closer to 0. And so we see, right, inside of these block diagonals, we tend to have lots of whites. And so that means we're making correct predictions. And outside of it, we have lots of blacks, so close to 0. And where we make mistakes, right, so you can see in the lower right-hand block, we make mistakes kind of across a single row. And if you look at the associated entries in predictive standard deviation, they tend to be high, right? They tend to be very white. So again, we do this over all edges. We take the Pearson correlation, and it's at 0.7. So we have a strong Pearson correlation between what we have access to in prediction, which is our predictive standard deviation, and what we're interested in, which is the error in our prediction. Okay, in closing, we analyze recovering graphs from nodal observations. We introduce DPG, which are simple iterations, to produce a true neural network when unrolled. The structure of DPG makes a parameter independently interpretable. We use this structure to construct informative parameter priors using priors on sparsity. By conditioning on the data, we produce a posterior distribution over our network parameters. And on unseen nodal observations, right, we push our posterior distribution through the unrolled DPG to produce a distribution over edges, right, our posterior predictive distribution, from which we recover our point at uncertainty estimates. And in the future, right, there's lots of things to do, but the most important one is scaling, right? So sampling based methods tend not to be super scalable, and so this is where people tend to turn to variational approaches to scale to much larger data sets and graphs. And if you'd like to know more, right, this preprint is on arXiv, and our code is public at the following GitHub link. And if you have any questions, feel free to shoot me an email, and I'd love to talk. Thanks.